All right, full screen there. Going to do some curve sketching and perhaps looking at how to visualize some graphs more quickly. Let's have at it. Going to start with simplest function, a constant, and build our way up to an x to the fourth polynomial and see what we can learn by doing so. All right, so y equals 5. I'm going to let x equal 0.01 to give a little feel for local behavior, near the origin. Certainly when x is 0, we can immediately figure out some values. Now, 5 is really y equals 0 times x plus 5. So it doesn't matter what the x is, you get 5, and that's why the graph looks like a horizontal line. Okay, and we don't have to write that. But if this was positive, we'd have a linear function increasing, and if that was negative, decreasing, and we're just right in the middle. No change. Okay, number 5 is not changing. Don't care what x value, no variability. So y equals 5 is a constant. Now we're going to graph y equals 2x plus 5. And I'm probably hearing you on the other end of the camera going, oh, I've done that. That's algebra 1. Yeah, but we're going to take a little turn here in a moment. Okay, so this is your mx plus b. And if you've been doing my videos, watching them, I'm not a fan of mx plus b. I think we should be writing it as ax plus b so that we get templative with ax squared plus bx plus c and ax cubed plus bx squared plus c, so on and so forth, cubics, quartics. And so I think we've established that y equals 5 is a horizontal line. 2x is an increasing line, and if you get them together, I'm sure your brain said, okay, let's go to 0, 5, and let's go up to 2 to 1. That's what our graph looks like. I think it's very helpful if you read polynomials backwards. If you read this as 5 plus 2x, then over here, 5 plus 2x. If you let x equal 0, you get 5 plus 0. If you let x equal 0.01, you get 5 plus 0.02. And we can start to see the change from this line to that line is 0.02. The change in x is 0.01. And we get a feeling for how the polynomial is changing at a 2 to 1 ratio. When you're looking at 0 and then you change a little, we refer to that as local behavior. If I could spell local behavior. Okay, let's just do that for shortcuts. It's when you start putting in bigger numbers that we end up with what is called end behavior. Okay, and the end behavior here is that this graph is going up. And we also know it's going up at a constant rate. Okay, so we've established a couple of terms, local behavior and end behavior. Let's continue. Let's look at y equals minus 3x squared plus 2x plus 5. And in this video, I'm trying to get you to read it backwards. Okay, so what do I see? I see 5. What am I doing there? I'm going up at 2 to 1, but this is going to do what? Have that tendency and the end behavior on this. All right, and we get a little view of the parabola from a slightly different perspective, where I know at 0, 2, I'm on the y-axis, and sure looks like my x value here is to the right, so it's positive, and we've been studying how to get that x value quickly and easily, minus b minus 2 over 3 times a, 2 times a, because I'm getting to a cubic soon, 2a. And we've looked at the geometric reasons why that's true in other lesson sets and in other videos. And so this thing turned pretty quickly, right? At what, 1/3? The 2's cancel, the minuses cancel. So x equals 1/3 is where that turned, and it happened pretty quickly. Now, if we look at the table values, and we're still looking at local behavior, right? Then put in a 0, you get 5, 0 minus 0. But if you put in 0.01, you get 5 plus 0.02 minus 0.0003. I did a little analysis there. I did change it to fractions. I think it's easier for you to see the fractions than the decimals in this case, but I went back to decimals. 2 100ths minus 3 10,000ths. Well, I got to get this common denominators. So it's really 200 minus 3 over 10,000, which is 197 over 10,000. And if I change it to decimals, it's 1.97 now. So I'm not going up a 2 to 1, but pretty darn close to it. Right? So it didn't matter. This term locally didn't really affect this polynomial all that much. This still dominates the change. And if you're seeing these numbers change, we talked about this in previous videos, please, give me a call. I'd like to have your number so we could chat. If you're seeing 5 to 5, if you're seeing some change there, just give me a telephone number and cell number and we'll have a little chat and take it from there. All right, so let's go to a cubic. All right, so let's go to a cubic. This is how it will be presented to you, but I think you should read it that way. And let's put a 0 in. 5, 0, minus 0. We've already established that. And 0 cubed is 0. Let's put 0.01 in. We've already established this, but we're also adding 0.001. Locally, that doesn't seem to be affecting the major change. Right? I mean, I'm still going up pretty close to 2 to 1, even with this term. So what could I do? I could take the 5, 0, 5. I know I'm going up. I know it's starting to bend. And what's the end behavior? Well, the end behavior is if we put 100 in here. Put 100 in here. That's still 5. That's 200. That is 4 zeros with a minus 3. So there's 4 zeros with a minus 3. That's got 6 zeros with a 3. With a 1, sorry. 6 zeros with a 1. You tell me what column dominates the numerics here. Yeah, it sure looks like the cubic. So I know this thing probably has a local min, a local max, probably does, but I'm not sure. But I do have a little feeling, a better feeling for this function, and I don't think we are changing too much in this area. And so I got a little feel for what the graph looks like. Now let's put it in graphing form because we have been playing with that, and it'll be good to see how much you recall. So we have established that at 0, 5, I'm going up at 2 to 1. I'm getting a bend, and I know I'm finishing there. So it would be nice if we had the point of inflection. And for the linear function, ax plus b minus b over a gives us where the graph changes from negative to positive or vice versa, positive to negative, depending upon the a value. For y equals ax squared plus bx plus c, we get ourselves the vertex x value at minus b over a, 2a. And for the cubic, it's minus b over 3a. And those are all about the geometry behind the algebra. Okay, this comes from completing the square, minus b over 3a comes from completing the cube. And if you want to see those geometric manipulations, go to the playlist and look at completing the cube. All right, and that explains why minus b over 3a is where this thing is going to change concavity, which is all about the rates of change, which is why we're looking at this and the way we're looking at it. Get a little deeper sense of rates of change. All right, so minus b, positive 3 over 3 times 1. Yeah, it changed pretty quickly right here at 1. 1 unit gave us that change. And so if we put 1 in, we get 1 minus 3 plus 2 plus 5. And it looks like we've got ourselves 5. Wow, it's the same height, 5. I have a feeling that there's some symmetry here, and we're going to get a 2 gets us a 5. I'm not going to look at it, but I do believe that's going to happen. Right? And we will look at it from a different perspective here in a second. So what did I do? I looked at 5 plus 2x minus 3x squared plus x cubed. We did that just a moment ago to my left, and now we're filling it in with more information. Okay, now what's the rate of change there? You've heard it for 3 or 4 days. Now the question is, can you recall how to find quickly the rate of change? And I'm not doing calculus here. I'm doing all the stuff that precedes calculus, why I think the cubic is the best function to study in high school math, the interplay of the different terms. But I hope your brain just said C minus 3AH squared. C was what? Looking up here, it's easier to look that way for A, B, C, and D. So we'll look here. So that's 2 minus 3 times A, which was 1. All right. 1 is in front of x cubed. And we found that 1 was the x value of the point of inflection. So 2 minus 3 sure looks to me like I'm going down at 1 to 1. So at this instant, I'm going down at 1 to 1. And that's actually a minimum rate of change for this function. Up, 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 0. Just like a roller coaster, this is where your stomach's falling out. That's where you're going down the chute fastest. All right. And there's lots to learn about that. And then I don't know what you remember, but we need frame of reference. So my frame of reference for that x value is 1. I know I'm to the left, and I know it's about the interplay of the rates. And I now know I'm going down at 1. So I'll put an opposite of that, positive 1 divided by 3 times a. And that's actually the x value. And this one is, and I'm not teaching this a whole lot right now. Right? Just planting some seeds, seeing it mechanically so that we can continue this discussion and eventually maybe look at where that comes from more deeply. All right, but that gives us that feel. All right, now from a different perspective, because once I saw 0, 5 and 1, 5, I thought 2, 5. Well, that looks like this, where you're going across and you're seeing 3 values. Well, that looks an awful lot like the work we do with roots. All right. So if I drop this down 5 units, I'd have roots at what? At 0, at 1, at 2. And we do a lot of work with that in algebra, more than maybe we need to, because I think this is more interesting, finding rates of change and looking at it geometrically. But we do a lot of that. So let's actually look at this from the factoring perspective, and then we'll get to the x to the 4th graph. So I'm going to go back to the original way it's written. X cubed minus 3x squared plus 2x plus 5. And I said you can put this in factored form. X times x squared minus 3x plus 2 plus 5. And now I can see that a 0 gets me a 5. Now the question is, what else gets me a 5? Well, there's your x times x minus 2 times x minus 1 plus 5. And now we have verified that a 2 gets us a 5. And I just thought it was interesting to see it from that perspective. So maybe factoring this will always get you the constant, and you can see some numbers. That's not a bad thing to know. All right, so let's get to the x to the 4th graph. And let's see what we can do to maybe, oops, I'm going to have to move Rene the cart here. There we go. And I'm going to have to bring this around my charger. Excuse me for the delay. But continuing our analysis, this is how it would be presented to you, but I hope we're looking at it from the 2 minus 6x plus 17x squared. Haven't got to remember to practice this a little bit more. Plus x to the 4th. And these should look like familiar numbers from what we did before, but I did 3 decimal places for more accuracy. But I hope you can see that this is still the dominant term locally, right? And I'm going down at 6 to 1, right? So I know where I start on the y-axis. I know I'm moving down at 6 to 1. Then I'm looking at the interplay. And each of these has less, right, effect on the changing y value. When I move from 0, initially, this is the most important term, and then they gain importance as we move in that direction. To the point where if we work end behavior, we can see the reversal of that. The reversal of that is the x to the 4th term dominates. Locally, the linear term, well, locally, 0, that's the term that matters. But as we move, that assumes more dominance. Okay, did I want to say something else there? I don't think so. So let's go over and see how we do with sketching. And then you can put it in a graphing calculator or Desmos, some online graphing feed, whatever app you want to use. But I'm going to graph this from what I see. So I see 2 on the y-axis. So I'm going to go right here, 0, 2. What else? I know I'm going down at 6 to 1. I know this is going to slow that decrease a little bit, but this is going to accelerate it. So I'm really not sure what's going on here, but I do know one thing, next to the 4th, going up on the right, and if I put a negative times a negative times a negative times a negative, I'm going up on the left. So my first thought was, okay, let's throw x equals -1, just to get a feel for this. Well, that's a positive, that's a positive, that's a positive, that's a positive, and that's a positive. Ah, so I get a positive number. Wow. And that's on this side, so that's actually taking me up. And what happens if I put -10 in there? I hope you say I get a bigger positive number. So I know the right-hand side is just coming down. That much I know now. And if I put the number 1 in, so I know where we are at 0, right? We're at 0, we're at 2. I wish I was reading this back. Well, I am reading it backwards, so I can do it that way. So I know I'm at 2, and then I know I'm subtracting 0, adding 0, subtracting 0, and adding 0. And if I put the number 1 in, I'm at 2, I'm at -6 plus 17 minus 5 plus 1. So this is definitely dominating quickly. So I think it's pushing me up almost immediately. A little bit of a wobble here, but pushing up almost immediately. And then if I put 10 in, all right, well, maybe 5, something like that. Maybe 5's an easy number to work with. I get 2 minus 30, 25. So 16 quarters is $4.25. So I think that's $4.25. I could be off on that. 125 times 5 minus 625, I believe. And 5 to the 4th, I think, is 625. Okay, I hope my math's right there. Okay, so we already have a tug of war here where these are balancing out. And so I think this term is still very dominant. I just think we're going up with a little bit of wobble. So that's what I think it looks like. And I'll go to Desmos, check it out, and hopefully with practice, get a little better at seeing the interplay of the terms. But I've got the end behavior. I've got the local behavior going down at 6 to 1. Now, I used to put these in graphing form, all right? And I've lost all that data. Went through 4th degree, I think up to 7th degree. 4th to 7th, right? Because the graphing form for this is based on minus b over 4a, which is completing the quartic, which I think is pretty hard to draw. Okay, but you can extrapolate, right? Minus b over a is the average of the linear roots, if you write ax plus b. Minus b over 2a is the average of the quadratic roots. Minus b over 3a is the average of the cubic roots. It's all about reshaping the geometry of these lines. You don't have to reshape a line, but a rectangle that doesn't have even sides, you can draw as a rectangle that does have even sides. And a cubic that doesn't have equal sides, you can draw one where it does. And that's where all of these minus b over blah, 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 a's are coming from. I think that's important to know. So let's just do one last problem here. Let's just graph a quadratic, but from the reading it backwards perspective. All right, textbook comes at you, 4x squared plus 8x plus 3. I like to read it this way. I'm at 3, 0, 3. I know I'm going up at 8 to 1. And I know that's going to make it happen faster. So I know it looks like this. It's coming. So there I am on that side. So I probably would have, if it was just me doing it instead of talking to you, I know I got a cup shape up because of end behavior. I know I'm on the increasing side because I'm going up at 8 to 1. So 0, 3, I look for these numbers first, and I also knew that, which means I have a negative x value. So I know, minus b over 2a, 8 divided by 8, 1. So that's going to be -1. And if you put -1 in, you get -8 minus 4 plus 3, -1. And you can get much quicker, faster, stronger, better, right, in your mechanics and hopefully conceptual understanding. Okay, and what we did before, we could put that in graphing form by writing it as 4x plus 8 times x plus 3. So what does that show us? Well, it always shows you that one of your roots to this, I'm making a rectangle there, right? And that's all about completing the square, but this is a rectangle with uneven sides, and I know 0 gets me no area, and I also see -2 gets me no area. Well, obviously, it's got to cut through -1. Right? So there's all kinds of different perspectives, and there's none that's better. There's some that help you do things more quickly, but all perspectives have equal weight in terms of what do you learn from them? And whatever you learn from them, hopefully you can use and get a little faster with all your calculations and maybe have a little more conceptual awareness. All right, so if you want to see completing the square, completing the cube, go to the playlist, and there you have the geometry of taking a rectangle and making it a perfect square with an adjustment, right? Taking a box where we don't have equal sides and making it a box that has equal sides. I'm not going to draw anymore. I'm starting to ramble. Okay, so hopefully that exercise might get you thinking a little bit. All right, see you in class.